What the heck?
Tagon.
Well, well, well. So it's come to this. I wore the garb of your soldiers so I could infiltrate your, shall we say, facility. And I'm going to plant this nuke on you. I wish you best of luck in response, because this is going to require at least 2 parts, because there's just quite a bit that I want to explain. Maybe even 3 parts, maybe even 3 if I manage to pull off the 3rd part. But I'm going to do something that I've been waiting to do for a long, long time, both to show off some cool ideas and to finally respond to your admittedly very good generalization. I'm going to be doing the inverses, the derivatives, and hopefully some form of integrals of power towers today. Well, the first part today, and so on and so forth for the next couple weekends. So today we're going to start with inverses, and we're going to need to sort of develop different kinds of functions to be able to actually adequately answer these questions. Because you can say solve for the inverse of x to the x using the Lambert W function, but the rest don't give way to that function, so you need to be a little more creative to actually even have a hope of calculating things about them. So what I'm going to do is I'm going to introduce some of the ideas of tetration and power towers, give some definitions that I'm going to just sort of use freely throughout these video series so I don't have to say the same thing multiple times, and sort of compactify the notation, because towers of x that are n tall, if you don't know n, it's kind of hard to write out 50 x's. But of course I want to speak about, the 50th tetration of x if I want to. And so we have to make some generalizations, wink, and define some new functions. So bear with me, it's going to seem very definitional for a while, but we'll be able to, using these extensions of relatively familiar functions, deduce facts that we also know to be true in a neat way. So today we're starting with the inverses, and next weekend I'm going to hit you with the derivatives. So let's get to it. Also, everybody follow my new dog on Instagram, @FluffyGus, @fluffy.gus. He is positively adorable, and I love him very much. So if you have a thing for dogs, you like dogs a lot, follow that Instagram. I'll link it in the description. Thank you. Also, but more importantly, follow my Instagram @WhatTheHectagon, of course. So let's get to it. Let's quickly just discuss operations. In a sense, you can start describing arithmetic operations as combining numbers in certain ways to achieve new numbers. Jens talks a lot about, or Flammable Maths talks a lot about, the suck function, so the successor to a number, right? So the successor to an integer a is a plus 1, right? It's the next number, so this is sort of the 0th operation, right? Suck a, of course, naturally. But of course this is a very slow, arduous process to add 1 repeatedly, so we want to think of a way to repeatedly apply this operation. So the first operation then is addition of any number. So we have a plus n, where this is the same as a plus 1 plus ... plus 1, where there are n ones, right? That's the first operation. It's repeated usage of the 0th operation, and that's how we're going to define each operation as we go down. So this is called usually succession, derived from what I believe are the Peano axioms, or is part of the model of arithmetic that is given by the Peano axioms. This is addition, of course. Now the second operation is going to be repeated addition. So we have n times a, which we define as a plus plus ... plus a, and there are n of them, right? So this is called multiplication. It's not too hard, right? These things also come with all of their own inverses, right? This is subtracting one. I don't know what that would be called. Pre-succession. Hand session. The opposite of a succession is a hand session, obviously. Addition, the opposite is subtraction, right? The opposite of multiplication is division. We're talking about sort of the forward operations as opposed to the backward operations. The third operation will be repeated usage of multiplication. So we'll say a to the power of n, which is understood as a times dot 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 times a. And there are again n of them. And this is called exponentiation. Kind of a large word. And from this point forward, the operations are named after the ordinal number that they represent, because we sort of ran out of creative words. And it's called tetration, where the Latin prefix tetra meaning 4. So the fourth operation is sort of a play off of the notation for exponents. It looks like exponents, but now the exponent is in the top left, and this is understood as a power tower of a's, right? A to the a to the a to the a to the a, etc., where that power tower is n tall. And it is not thought of as this. This is not this, where it's like you're working from the left to the right, because all you could do in this case would just be multiply all the a's down, and then you end up with a to the power of n minus 1, and that's simply just one thing of tetration and then an exponent. So no, we want to work them from right to left. In that way, we are able to write this thing as a to the power of the n minus first tetration of a. So you're sort of working your way from the rightmost a and working your way down, which has the effect of making tetration of relatively, I would say, large numbers, like above a certain point, has the effect of making them grow incredibly quickly. You can learn about sort of the basic usages of tetration in Grant Sanderson's, or 3 Blue 1 Brown's, recent live stream or lockdown math session that he did about tetration. It's very, very cool. I recommend watching all of them. There's almost certainly no way that any of my fans aren't also fans of his. That would be quite a shock. But if you aren't, please check him out. One of my favorite YouTubers by far. Like, he needs my support, right? And so we could keep going with this. This is called tetration. Just like exponentiation has two inverses, right? It has the nth root to get at the base, and it has the logarithm to get at the power. Tetration also has two inverse operations. It has the super root, which gets at the base, and it has the super logarithm, which gets at the, I would say, the height. I believe this is called the height of the tower. There's pentation, which is repeated tetration, and you would put the n in the lower left. There's other notations as well. There's Knuth arrow notation, but we're not even going to get to the fifth operation. We're just going to talk about tetration today. Now this is quite a slippery bastard of an operation, because when you try to map this, like what the xth tetration of e is, sort of the tetration analog of e to the x, you get this incredibly chaotic function in the complex plane specifically. And it's very hard to wrap your mind around and understand. We're going to have the base be the varying amount, not the height of it, because it's a little easier to understand in that regard, and it's sort of more familiar based on stuff that Jens himself has actually been talking about lately regarding integrals over x to the x and its different variations. As well as a cool question about x to the y equals y to the x and what values that takes on. So let's get into the meat of the subject then. So we want to talk about tetration as a function of x. So the base, much like polynomials with fixed powers, right, and moving bases, we're going to talk about tetration with fixed heights and moving bases. Beginning of tetration is, what would this be? The second tetration of x. I should probably get a darker pen. And we mean this, of course, to be x to the power of x. Of course, we understand that if we then did x, the third tetration of x, we would have x to the x, or more precisely, x to the power of the second tetration of x. And of course, because we can sort of recursively define things like this, we would want the first tetration of x to be the thing that's in the power of the x here. Of course, it's just x, which leads us to the conclusion that the first tetration of x must just be a single x, right? That seems to make sense, right? A power tower of height 1 would just be x. And in general, like we said earlier in defining tetration, we can write the nth tetration of x as simply x to the power of the previous tetration. So x to the n minus first tetration of x. So that allows us to move forward. So let's see if we can devise a way that we can move backwards, right? So we want to generalize a way of moving backwards to maybe find out if we can extend this definition of tetration to lower heights, right? Maybe even negative heights. Much like we can do negative exponents as an extension of the original definition. Let's see how far backwards we can go. Well, it's not too hard to see that if we have the nth tetration of x being x to the power of the n minus first tetration of x, we can then take the logarithm of both sides, right? The natural logarithm. So we get the log of the nth tetration is equal to, we bring the power down using the rules for logarithms, right? We get the n minus first tetration of x times the logarithm of x. Then to sort of get at the previous one, the n minus first tetration, we just have to divide by log x. So we get that the log of the nth tetration of x divided by the log of x is equal to the n minus first tetration of x. So there's our way of moving backwards, right? That's the way we can get at the previous tetration by knowing the one after it. Let's say we start with the second tetration. So we want to see if we can figure out from this principle what the first tetration is. We already know it's x, but let's just see that it works. So let's plug in 2 for n, right? And we get the 2 minus first tetration, which is of course the first tetration, and let's see what this gives us. So we know that the second tetration is x to the x, so we have log of x to the x divided by log of x. Using the power rule for logarithms to bring that x down, we get x times log x over log x. Naturally, the logarithms cancel. Naturally, the natural logarithms cancel, and we're left with x just like we devised before. Correct? Does that make sense? Of course, we know that we can actually really technically use this as a recursive formula as well, because all we have to do is now, if say we wanted the 0th tetration of x, all we have to do is ask, well, we know that the first tetration is going to be x to the power of the 0th tetration. Here we have x, this is x to the power of 1, which means that the 0th tetration of x must be 1, no matter what the base of the tower is. We know that the height being 0 means we'll just get 1. So that's our hypothesis. Let's test it in the formula that we just derived, where we were able to derive the previous tetration using this formula here. So now we know that the first tetration is just x. So we know that if we want to find the 0th tetration, we just need to plug 1 in for n there, and we get the log of the first tetration of x divided by log of x. We know that the first tetration of x is x, so we get log x over log x, which is of course 1. So this is a tetration of x with height 0, right? That's what that means. Of course, we can go farther. Let's see what happens. So if we plug in 0 for n here, we get log of 1, right? Because the 0th tetration of x is 1 over log x. The logarithm of 1 is 0 over x, and so we just get 0. This is the negative first tetration of x. So a power tower of height negative 1 is always 0. That's what that tells us. Very interesting, very odd. And of course, we can try to go to negative 2, but you'll probably see the problem in that, because we'll need to do the logarithm of the negative first tetration of x, which requires us taking the logarithm of 0, which is undefined. Undefined, right? So there is no power tower of height negative 2 or negative 3 or anything like that, much in the same way that you can't take the factorial to negative integers, right? So it's sort of a similar idea, right? We hit a roadblock, we hit an undefined point, and it's not anything that's like an indeterminate form, right? Log of 0 really is undefined, because there's nothing that we could raise, there's no power we could raise something to get 0, other than starting with 0, so you sort of lose all the information. So the best we can do is a negative first power tower, and that will actually come in handy later on when we're trying to discover inverses, etc., etc. Given that these are the first two power towers, right? These don't have inverses, right? These are strictly constant numbers, so they don't have well-defined inverses. even in the sense of like being a multi-valued function. It's just you're talking about two flat lines, y equals 0 and y equals 1, and inverting them just gives you x equals 0 and x equals 1. And so I guess you could say those are the inverses, but they're not really interesting functions in the sense that we generally like. So the best place to start when talking about inverses is naturally at the first tower power. I keep saying tower power. If I ever say it and I don't realize it, just understand that I mean power tower. So if we take a look at the first tetration of x, which is of course just x, it's not too hard to see what the inverse of x is. The inverse of x is x, right? By the way, so that an easier way of writing the derivatives of these functions or the inverses of these functions, we're going to do t sub n of x, or maybe even simply just t sub n if I'm feeling lazy. So these two things will be equivalent, and this will always mean the nth tetration of x, right? So these all mean the same thing, and I will use them interchangeably depending on maybe how it looks or how easy it is to notate or express an idea. If I'm trying to talk about the derivatives or inverses of the tetration, I'm going to use this or this because this sort of lends itself to putting a -1 or derivative indices like that. So, or powers of this function, in fact. So this will be the more common notation, and I'm actually gonna start using it now just to get you used to it. So that would mean, if we just go back real quick, that t sub -1 of x equals 0 because it's the negative first tetration of x, and t sub 0 of x is equal to 1 because it's the 0th tetration of x, and those are the things we just talked about. But we're gonna start from the first one, right? So it's pretty clear that if we say that y is equal to the first tetration of x, we know that that's equal to x. X is a straight y equals x is sort of the point of inverses, right? I guess I should say the line of inverses. If you reflect over the line y equals x, you get the inverse function of what you're talking about. So sort of by definition, it's its own inverse. So the inverse, this implies that the inverse of the first tetration of x is also x, right? So that's not too crazy. The second one gets a little hairier, just a little hairier, but we can still do it with things that we're familiar with. So if we say that y is equal to the second tetration of x, which is x to the x, what is, pray tell, the inverse of this function? So I'm going to solve for x now. So we have y equals x to the x. So to try and attack the x's, I should probably take the logarithm of both sides to start. So I get log y is equal to x times the logarithm of x, right? Not too difficult. But now we need sort of something creative, right? So these are two very, very not very friendly functions, right? One's a polynomial, one of them is a logarithm, which is a transcendental function, not algebraic. So we need a different kind of function. Now, the crux of the argument here is to realize that we can write this as log x times e to the power of log x, because that's what x is, right? X is e to the log x, because they are inverse functions, they cancel and we get x back. But now, take a look at what we have. We have something times e to the power of something, and given all the videos that I've been making recently, this should scream at you what we should be using. We should be utilizing the Lambert W function. So we should take the Lambert W function of both sides, so we get w of ln of y is equal to w of this thing, but because it's of the form a times e to the a, we just get a back, right? Because w is the inverse of that function. So we get log x. Now to finally solve for x, we just need to exponentiate both sides, like so. And we get that x, after having solved for it from this relationship, x is e to the w of the natural logarithm of y. Now we can actually rewrite this as log of y divided by w of log of y. And this just comes directly from what we understand about the w function, right? Inverse, I'm just going to do it like this, of x times e to the x, right? So I'm saying that this is the inverse function of that. We know that therefore x must be equal to w plugged into this function because they undo each other. Dividing w of x on both sides, we get this pretty familiar relationship, right? E to the w of x is equal to x over w of x, which is why I'm able to say that e to the w of ln y is equal to ln y over w of ln y. So that's all I wanted to say there. Of course, we don't want x as a function of y, we want to write the inverse function as a function of x. So all we have to do is swap x and y now, and we get that the inverse of the second tetration of x, the second power tower, e to the Lambert w of ln of x. But as soon as we try to extend this to the third tetration of x, we immediately run into a problem, because we don't have a familiar function to look to solve for it. By the way, because we're finding we're solving for the base, right? We're solving for x in this case, as opposed to the height of the tower, which is 2. We're not doing the super logarithm, we're doing the super root. So this is also called the super square root of x, sometimes notated like that, because it undoes the second power tower of x, right? So there's an implied 2 there, just like there's an implied 2 with square root of x, right? We don't write the 2 because we sort of assume it's there. And then we write other numbers when we want to take like the cube root or the fourth root. And so anytime you solve for the base of a power tower of height n, you are taking the nth super root as opposed to the regular nth root if it were x to the n, because we're talking about the nth tetration of x instead of exponentiation. So let's quickly take a look at the third tetration of x, right? This is x to the x to the x, and we solve it from right to left, right? So this is the same thing as x to the power of the second tetration of x. And try as you might, there's no real way to utilize the w function to invert this function. It's a futile effort indeed. So we need something different. We need a new idea. How could we address this problem with quality mathematics? Well, before we do that, we got to try something a little radical, right? So we can't do the third power tower. It's not too hard to see that we won't be able to do the fourth power tower, or the fifth, or the sixth, etc., etc. But as soon as we let that carry on forever, and we have an infinitely tall power tower of x, it becomes trivial. Let's say we have the limit as n goes to infinity of the nth tetration of x, and we'll say that this could either be written as like t sub infinity of x, perhaps we'll just call it t of x. Maybe we could write it as the infinite height power tower of x, you know, literally think of it as x to the x ... where it goes forever in up and up and up. And the reason that this becomes trivial to solve, in the sense that these are trivial to solve, is because we can recognize that inside this infinite power tower of x is an exact copy, just like Grant showed in his video. So if we call this y, right, y equals x to the x to the x ... right? And we notice that if we cover up the first x, we have an infinite power tower, again, right there, right in front of us. Because it's still infinitely tall, and only because it's infinitely tall, we can call this other part with the x at the bottom here, we can also call it y, right? So this is x to the power of y. If we define this infinite power tower and call it y, then it must be the case that it is the same as x to the power of y. So if we raise both sides to the power of 1 over y, we end up with the fact that x, the original input of this function, is equal to y to the power of 1 over y. Now that tells us something very interesting, right? That tells us that because we have x solved in terms of y now, we see that the inverse of this infinite power tower of x must be x to the 1 over x. Because when we solved for x as the input in terms of y, we got y to the power of 1 over y, which means swapping their roles, we get that the inverse of this function must be x to the 1 over x, which is very weird. But now, because we have this as a simple, like, one power of another in terms of x and y, we can just utilize the w function again. It's actually not too hard. All we have to do is take the logarithm of both sides like we did before. So we get log x equals 1 over y times log of y, right? And now what we want to do is we want to make these things appear the same, just like we had x times log x before. We're going to want this to be 1 over y in here. So we need to multiply both sides by -1 so that this -1 on the right side can go into the logarithm as a power, right? So that just falls into the logarithm as a power of y, but what's y to the -1? It's 1 over y, right? And now doing what we did before, we can rewrite 1 over y as e to the log of 1 over y. Now we can do the w function on both sides again, right? It's not too hard to see. We can just apply w on both sides. We get that w of negative ln x is equal to, well, the w and the something times e to the something cancel, and we're left with log of 1 over y, which is the same thing as negative log of y because of the power rules for logarithms. And again, we can simply, we'll multiply the -1 to the other side, and we'll just exponentiate both sides. E to the ln y gives us y like we wanted. And given the fact that we can utilize the thing I determined before to get this answer, we actually end up with a very interesting expression. We end up with we end up with w of negative ln of x divided by negative ln of x, which actually tells us that this function, this infinite power tower of function, is almost identical to the inverse of the second power tower of x. Because take a look, if we plug in 1 over x here, then that 1 over x brings a negative out to the front of the logarithm, and it brings a negative out to the front there. And then if we reciprocate that, we end up with this expression right here. So what does this tell us? That tells us this very strange theorem. Let's call this, so we can call this, a theorem, I guess. That tells us that the infinite tetration of x is equal to 1 over the inverse of the second tetration of 1 over x. That's to say that if we plug 1 over x into this thing and then reciprocate it, we get that, right? This is not the inverse of the infinite tetration. This is the infinite tetration of x. Because remember, before we determined that the inverse of this is actually 1 over x. So, I'm sorry, x to the 1 over x. But yes, this is true. These are two theorems that we just derived. So it's a little weird that we can attack the first tetration, the second tetration, and then none of the other finite ones, none of them, using the w function or any other functions that we know, until we get to the infinite power tower of x. Then we can sort of reduce this because we have a repetition of the whole function inside of itself, and then use that trick to deduce what the function must be equal to in terms of other things that we know, and we can find its inverse, both of which are just very, very strange. But what of everything in between, right? We want to understand the third power tower, the fourth, the fifth, etc., the minor fourth and the major lift, and all that. Let's see if we can get at the problem in a different way, right? So we have a good understanding of the negative first, zeroth, first, second, and infinite power towers, as well as the inverses of the first, second, and infinite power towers. Let's see if we can figure out all the integer-valued power towers in between. So we need to sort of define a new idea. So the Lambert W function is sometimes called the product log because it's the inverse of x times e to the x, right? It's a product of something with e to the x, and so it's sort of the simplest idea of what that could be. It's just x times that. But we don't want to just stop at x times e to the x. We want to extend that idea. So let's say we define, and I'm going to use epsilon here. I need a new pen. So let's define epsilon 1 of x to be this familiar x times e to the x. And we understand from all of my videos and reading Wikipedia articles and etc., that the inverse of this function is the Lambert W function, right? At whatever branch you pick, we're really just going to think about the principal branch, but this is sort of what it is, right? And this is sort of where our intuition for the inverses of the power tower stops, because we don't have the function necessary to actually deduce what the inverse could be in terms of functions that we know. So we sort of have to define new functions into existence. So what I want to do is generalize the idea of this thing right here. I want to sort of make a power tower out of it. Because let's say we consider, instead of x being our variable, let's consider e to the x to be our variable. Because in a sense, this is just x times the first tetration of e to the x, right? Because the first tetration of something is just that thing. We deduced that before. And so because there's just one e to the x, it's the first tetration of that thing. So that's an interesting way of thinking about it. So logically, what would epsilon 2 be? Epsilon 2 would be x times the second tetration of e to the x. So it would look like x times e to the power of x, all raised to the power of e to the power of x, right? Because we're tetrating e to the x. But based on the way powers work, I can simply multiply this e to the x by the power here, which is x. So I will get this funky looking thing, which is sort of looks like a continuation of this. It's x times e to the x times e to the x. And so it's sort of like a double-tiered version of this function right here. And in general, epsilon n of x will be x times the nth tetration of e to the x, which will look like x times e to the x times e to the dot dot dot, I guess x times dot 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 dot, all the way e to the x, and there are n e to the x's. And of course we're going to eventually carry this on forever and ever. But let's sort of see what these things are. So I'm going to define the inverses of each of these things to be like an analog of the w function, but I can't use w sub 1, w sub 2, w sub 3, because that could be interpreted as the notation for the different branches of the w function. Instead, I'm going to utilize the notation of another Greek letter, which looks like a W. I'm going to use the little omega letter. So the inverse of the first epsilon function, or the inverse of the nth epsilon function, is going to be called omega sub n of x, which tells us specifically that the inverse of the first epsilon function, which we know to be the w function, is from here on out, unless I want to specify otherwise just to show you that these are related, is going to be called omega 1 of x, right? So these two things are now synonymous, right? And the inverse of this is omega 2, and the inverse of this is omega n, right? So this is sort of the definition of these epsilon functions, which is this power tower version of e to the x times x out the front, and is sort of a generalization of this multiple layers of x times e to the x, etc., etc., so we can have sort of a generalization of the w function to higher and higher power towers like so. Essentially what it is however many e's there are in this stack is the same as the index of the tetration, and will be the same as the index of the inverse function when we talk about it. So let's go backwards. Let's see if we can do what we did before with the power towers. Find the 0th epsilon function, the 0th, the negative first maybe it exists. Let's define them into existence, right? So we have epsilon 0 of x. We could just utilize this definition that we have of the nth epsilon function, right? This is going to be x times the 0th tetration of e to the x. And what was the 0th tetration of anything? The 0th tetration was 1. So this is just x times 1, which means that it's x. So just like the first tetration of x, we have x. And just like the inverse of the first tetration of x, omega 0 is the inverse of x, which means it is also just x. So I hope that's clear, right? This is the inverse of epsilon 0. By definition, right? The nth omega function is the inverse of the nth epsilon function, which is this power tower version of the thing that we get the w function from. So I hope that's clear. We can also try the negative first one, right? But we see we run into not a problem, but it doesn't amount to much, because what's the negative tetration of something? It's just 0. So this becomes 0 times x, and it's 0. And then we have to stop there because the negative second tetration of anything is undefined, and so this is the bottom, right? There's no inverse of y equals 0, so we sort of have to start at the 0th epsilon function if we want to talk about anything meaningful. So of course we can just write that up here as part of the collection, right? Just because it's a silly example doesn't mean it shouldn't be part of the collection. It's all in the family. So this is equal to x, or x times the 0th tetration of e to the x. And the inverse of it is just x, of course. The inverse of this is the w function, or omega 1. The inverse of this is omega 2. The inverse of the nth epsilon function is omega n. These are all the definitions that I was talking about. So let's carry this on forever and see what we get when we let n go to infinity. So we're going to have an infinite power tower of e to the x there. So we have the limit as n goes to infinity of epsilon sub n of x, which again we can either write as epsilon sub infinity of x, or maybe just epsilon of x, because, you know, none of them have no index, so we can just save the one that doesn't have an index for the infinite case. And this is, of course, x times the infinite tetration of e to the x. We were able to show that the infinite tetration of x was equal to w of negative ln x divided by negative ln x. So we can utilize this, right? The infinite power tower of x was equal to this function in terms of the w function. So we can utilize this to solve for this. But remember, I'm trying to get used to the notation of the omegas, so this is omega 1, right? The w function is by definition omega 1, the inverse of epsilon 1, which is this function here. Cool? So we can utilize this to solve for this by simply plugging e to the x into these things right here. So watch what happens. We end up with something kind of neat, right? We get x times omega 1 of negative ln of e to the x divided by negative ln of e to the x. Of course, ln of e to the x is just x, because they're inverse functions. So we just get negative x here inside of the omega 1 function, and negative x in the denominator. So this becomes x times omega 1 of negative x divided by negative x. Of course, the x's cancel, and we're just left with negative omega 1 of negative x. Or, if you'd like the w function more, we can simply write this as negative w of negative x, which is very weird, right? We know that the w function is the inverse of epsilon 1, but epsilon infinity, the function itself, not the inverse of epsilon infinity, the function itself, where this power tower of e to the x's goes forever, is negative omega 1 of negative x, which is just odd, very strange. But of course we can then find what omega infinity has to be, right? Because omega infinity is just going to be the inverse of this function here, right? Because omega infinity is the inverse of epsilon infinity. So we can just set y equal to this thing, solve for x, and we'll get omega infinity, right? Just to be clear, epsilon n is x times the nth tetration of e to the x, which gives you this power tower. Epsilon 1 is this function that we're all familiar with, and the omega n's are the inverses of these functions. In particular, omega 1 is the w function, because it's the inverse of this function that I'm calling epsilon 1. All we have to do to find the inverse of epsilon infinity, namely omega infinity, is to set this equal to y and solve for x. And that's not too hard, so we simply do y equals negative w of negative x, multiply both sides by negative 1, and then do both sides times e raised to both sides, because remember that's the inverse of that's what the w function is the inverse of. We need to apply epsilon 1 to both sides of the equation. And we end up with the result that negative x is equal to negative y times e to the negative y. Multiplying negative 1 on both sides, we see that the inverse function to epsilon infinity is y equals x times e to the negative x. So we get y equals x times e to the negative x, which you could sort of think of as x times e to the x times e to the negative 2x, right? Because these would combine to give us negative x in the power, which I suppose you could write as e to the negative 2x times epsilon 1, right? Because this x times e to the x is epsilon 1. We're just utilizing the definition that we were given. Strangely enough, epsilon infinity can be put in terms of the inverse of the first epsilon function, and the inverse of epsilon infinity can be put in terms of the first epsilon function, which is very analogous, very, very analogous to how the inverse of the second power tower could be put in terms of the w function, and the infinite tower power could also be put in terms of the w function. Whereas the inverse of the infinite power tower could be put in terms of this weird version of the second power tower because it was x to the 1 over x, right? So there's got this weird marriage where the base case, the standard base case, and its inverse sort of swap places when you go to the infinite case in both of these instances. And it's not that much of a surprise because the definition of these epsilon functions is in terms of power towers of something, so that's not surprising that they have that same aspect. But the fact that they have that aspect at all is what's a little weird. The tool that we're going to utilize now is these omega functions, because they are the inverses of all of these epsilon functions. And so now we're going to come up with a general way of expressing the inverses of the power towers, right? But we need to be a little clever. Notice that the inverse of the second power tower involved the first omega function, which is the w function that we're all familiar with. And that trend will continue. But first we have to sort of consider the nth case, right? The nth power tower of x. So I know this has all been very definitional at first and seems a little abstract that we're just sort of defining these things into existence, but all of this will be helpful when it comes to compactifying our expressions. So let's just quickly review. So now that we've established all of these weird relationships, quickly recap everything that we've learned and established. So, to start as low down as we can, we define the nth tetration of x to be the same as x to the power of the n minus first tetration of x, and the lowest one that we have is the negative first one. So we may as well start there, right? T sub negative 1 of x equals 0. And starting there defines everything after that, right? Because the 0th tetration will be x to the power of 0, which is 1. The first tetration will be x to the power of 1, which is x. The second tetration will be x to the power of x, which is that power tower, right? So this is sort of the definition of the nth tetration of x. And we were able to show that the inverse of the second power tower was the natural logarithm of x divided by w of ln of x, but I'll use omega 1. Or we could write that as e to the power of omega 1 of ln of x, right? We were able to deduce that, and remember, omega 1 is just the w function that we're familiar with. And we were also able to deduce that the infinite tetration, not the inverse of it, but the function itself, was equal to omega 1 of negative ln of x divided by negative ln of x, which is the same as 1 divided by the inverse of the second power tower of 1 over x, right? Taking this transformation of this function here. And we were able to deduce that the inverse of this infinite power tower is simply x to the 1 over x, which I suppose you could write as 1 over x to the power of negative 1 over x, right? And then sort of do the same thing where we had like negative w of negative x before. But the point being is it's got this weird inverse. It's that this strange function is the inverse of x to the 1 over x. And then we defined these other functions into existence, these epsilon functions, right? Epsilon sub n of x was x times the nth tetration of e to the x, which gave us, if we picked n to be 1, it gives us x times e to the x, of which the inverse is w of x, but we called that omega 1, sort of to have this generalization. And we defined those inverses of each of those functions to be these nth omega functions, right? In particular, we had epsilon 1 of x was x times e to the x, which tells us that the inverse of epsilon 1 is omega 1 of x, which we know to be the w function, right? I'm going to keep repeating these things so that it's absolutely clear to you where I'm getting these things from. And we also were able to deduce some facts about these infinite epsilon functions. So epsilon infinity, we learned, was the same as negative omega 1 of negative x, and that the inverse of this function, the inverse of epsilon infinity, which we called omega infinity, is actually just x times e to the power of negative x, right? Which is sort of the same weird trend that we have here, where it's sort of in terms of a weird version of a lower index, right? This is sort of a weird version of the second power tower of x, and this is sort of a weird version of the first epsilon function, right? So there's the trend there, right? And so this is just a recap of what we've been able to deduce about these defined functions, and it's sort of interesting that they have these relationships in the infinite cases, and that'll sort of pop up later. But now let's talk about maybe finding the inverses of all the power towers for heights 3 and above. Obviously stopping short of infinity, we've already figured that part out. We'll have to be a little creative though. So before we try to think in general using the epsilon and omega functions that we've just defined, let's consider first just a single example. So we know how to invert the second tetration of x. Let's see if we can figure out the third using these functions that we've defined. At first we want to try and isolate x and solve for y in terms of x, right? But it's not really clear how we would do that given functions that we're familiar with, but we have to start somewhere, right? So maybe we'll just start by taking the natural logarithm of both sides. So we get the natural logarithm of y, and then when we take the natural logarithm of the right side, the power comes down out into the front, and we get x to the power of x times the natural logarithm of x. Now, since we have the idea of maybe using these extended e to the x functions as inverses, or utilizing the inverses of those to help with these tetrations, we might try converting this x to the x into something else. So I'm going to write this as e to the power of the natural logarithm of x to the x, right? Because those functions are inverses. This implies that the natural logarithm of y is equal to ln of x times e to the power of the natural logarithm of x to the x. And this is sort of similar to what we had to do with the case of just x to the x, right? We ended up with ln x times e to the ln x, but it's like we have one more step going on here. So because we're taking the natural logarithm of this expression, the power can come down, so we can rewrite it as such. And here is sort of the one that we had before, right? When we were just doing x to the x, we ended up with x times ln of x. And again, we can rewrite this x as e to the ln of x. So this can be rewritten as ln of x out the front times e to the ln of x times e to the ln of x, right? Because x can be written as e to the ln of x. And you'll see that we have this funky stacked exponential function, right? You can't really see it there. Hang on. Let me adjust the camera. There you go. So yeah, we have this stacked version. And notice, this is just the second epsilon function with the natural logarithm of x plugged into it, right? This was the definition of the second epsilon function. X times e to the x times e to the x, which implies that this is just epsilon 2 of the natural logarithm of x. So of course, to get at ln of x, we should apply the second omega function to both sides of the function, to both sides of the equation, right? Because we defined the inverse of the nth epsilon function to be the nth omega function, right? Where omega 1 in particular was the w function that we're all familiar with. So we should apply omega 2 to both sides, and we end up with the conclusion that omega 2 of the natural logarithm of y is equal to log x, because it cancels with log x, or it cancels with this type of function, so we get log x. And of course, to get at x, we simply exponentiate both sides, and we end up with a familiar looking expression, right? We get that x, because e to the ln of x is x, we get that x is equal to e to the omega 2 of ln of y. Of course, to put this inverse function as y as a function of x, we simply exchange the x and the y's, like so, and we get the inverse of the second tetration function. So t2 inverse. I'm sorry, this is t3. My mistake. This is t3, right? Because it's a stack of 3 x's. The inverse of the third tetration function. And you may recall from before that the inverse of the second tetration function was e to the power of omega 1 of ln of x, which, of course, I'll keep saying it, we understand that omega 1 is just in particular the w function. And of course, I picked omega because it looks like a little w. I just wanted to pick a different letter so that it didn't look like I was talking about branches of the w function. Let's see if this works for the lower one, right? So let's consider the inverse of t1. Well, we know that the first tetration of x is just x, so the inverse of that is also x. So we should be able to apply the 0th omega function to this, and we should be able to get x out, right? So this should be equal to e to the power of the 0th omega function, if the pattern holds, of ln of x. But remember, epsilon 0 was again just x, which means omega 0, being the inverse of epsilon 0, is also just x, which means we're plugging in ln of x into the function x. So this is just e to the ln of x, which is precisely x. So the pattern does in fact hold, and there's no point in doing inverses of the 0th or negative first tetration of x, because those are constants, so they don't really have well-defined inverses. But essentially the pattern holds. So the hypothesis that we might have is that the inverse of the nth tetration of x, when put in terms of these epsilon and omega functions, is simply going to be e to the power of the n minus first omega function of the natural logarithm of x, right? Because notice this is the first tetration inverse, and it's the 0th omega function. The second tetration inverse, the first omega function. The third tetration inverse, the second omega function, right? So we should be able to prove this expression without much trouble. So let's do that. And it's actually really easy. You can do it with showing with an n height power and rearranging each expression, but it's actually way simpler than that. So let's take a look. So let's consider y equals the nth tetration of x. So this is t sub n of x, which is the same thing as the nth tetration of x, which you could imagine is a tower of x's that is n tall, correct? So let's say we take the natural logarithm of both sides, just like we did in the 2 power tower and the 3 power tower case. So we get ln of y is equal to, and this giant power comes down, right? We get the n minus first tetration of x, which is this whole thing right up here, right? Because that's n minus 1 x's. I hope that's clear, right? The whole tower is n, so starting 1 up must be n minus 1, right? So this is going to be the n minus first tetration of x times the natural logarithm of x, because this was the power of x inside the logarithm, right? So it comes down. And we could rewrite this like so. We could rewrite this as the natural logarithm of x times the n minus first tetration of x, like I wrote like this. But here's the thing about x's. We can rewrite it as e to the natural logarithm of x, right? Because those functions are inverses. So we get ln x times the n minus first tetration of e to the power of the natural logarithm of x. But this should look familiar based on definitions we had before. Remember, what was the definition of, say, the n minus first epsilon function? The n minus first epsilon function of x was precisely x times the n minus first tetration of x, which is to say that this is the n minus first epsilon function with ln of x plugged into the input. So this is epsilon n minus 1 of ln of x. So of course, if you want to cancel this epsilon n minus 1 function, you need to use the omega n minus 1 function. So we have to apply omega n minus 1 to both sides, and we get omega n minus 1 of ln of y is equal to ln of x. Exponentiating both sides, we get that x, after solving for it in terms of y from the nth power tower, we get that x is equal to e to the omega n minus 1 of ln of y. Of course, we would want to exchange x and y to put the inverse function in terms of x, but this essentially proves the theorem that we just stated, right? It proves the fact that we can put the inverse of the nth tetration of x in terms of the n minus first omega function that we defined before, right? So this is sort of a cool way of, I guess it's more or less defining the function into existence, but it's essentially giving it a name instead of it just being this mysterious collection of or you know, whatever. So this would be the nth super root of. So let's switch x and y. So we get that the inverse function of the nth tetration of x is equal to e to the power of the n minus first omega function applied at the natural logarithm of x. And this is what you may call the nth super root of x, right? The little s subscript means super, because it is undoing the nth power tower of x, right? You're finding the base, right? So if you were asked, you know, given 2 to the fifth tetration of 2, or I'm sorry, you were told that 2 is equal to the fifth tetration of x, you would have to take the fifth super root of 2 to get that number, the base of this power tower, or you'd have to do e to the omega 4 of ln of this base to get the number, or you know, to reverse it to get the number out. And so this is a good way of defining the inverse function. It's a unique way of doing it. And I'm not sure at all if this, you know, because these are each defined in sort of an integer way, I don't know that this necessarily gives us a way of extending the definitions beyond integers, but it might be worth exploring. I don't know that this necessarily highlights anything new, but it's certainly a way of using other functions that we can construct, like these power towers of e to the x, to sort of define what these inverse functions are. Now that we've been able to talk about a way of defining the inverses of these functions, maybe we could talk about the derivatives. Right, so the first tetration of x is just x. So of course the derivative of that is just 1. And the second tetration of x is of course x to the x. So the derivative is a little harder to find out, but you can do implicit differentiation, taking the logarithm of both sides, etc., and you can quite easily come upon the conclusion that the derivative of this is x to the x times the quantity, the natural logarithm of x plus 1. It's not very difficult, it's a little puzzle for you. And this is quite an immediate jump in complication, right? It goes from just 1 to this thing right here. And the ultimate test of these inverse functions, these epsilon functions, would be to see if they actually work in the infinite case, right? So what were we able to show? We were able to show that the infinite tetration of x was equal to w of negative ln x divided by negative ln x, and that the inverse of this was equal to x to the power of 1 over x, right? Quite interestingly. And this should be equal to e to the omega infinity minus 1, which is of course still infinity, of ln of x, right? So I should be able to utilize the infinite omega function to prove that. So let's see, what was the infinite epsilon function? The infinite epsilon function of x was in particular negative omega 1 of negative x, right? You could put the infinite epsilon function in terms of the inverse of the first epsilon function, and likewise the infinite omega function, which is the inverse of the infinite epsilon function, was in particular x times e to the negative x, right? This is the inverse of the infinite epsilon function, which was that sort of combination of x and e to the x as a power tower, right? So this just goes forever like that, an infinite power tower in that way, sort of a generalization of x times e to the x. And so what I'm saying is if I were to plug ln of x, if I were into this and then raise e to that power, I should get x to the 1 over x. So let's see if that actually works. So we're going to do e to the power of ln of x times e to the negative ln x. And that should give us x to the 1 over x. So we do our little maneuvering of powers. So I can write this as just e to the ln x to the power of e to the negative ln x. Now we can bring this negative into the ln x to make it 1 over x, and I think you can already see the magic happening, because e to the ln x is just x, and e to the ln of 1 over x is 1 over x, and there we have our inverse of the infinite power tower, the infinite tetration, just as I said it would, using the exponentiation of the corresponding omega function and with the natural logarithm as an input. So it does in fact work. Now for a preview of the next lecture in this series on tetration, we're going to ask ourselves about the derivatives of these functions. So of course the derivatives of, since the negative first tetration equals negative 1, and the 0th tetration equals 1, we can clearly see that the derivatives of these functions are both equal to 0, right? So not very interesting, not quite that interesting. And since the first tetration is equal to x, this implies that the derivative of the first tetration is not surprisingly just 1, right? Because the derivative of x is 1. And as soon as you go to the second tetration, this is where things get a little hairy, so you have to sort of use implicit differentiation and be a little clever. So we have x to the x, and if you do this, we end up with x to the x times ln of x plus 1, which is quite a jump in complexity, right? From 1 to x to the x times the quantity ln x plus 1. And you might even think, oh, I'm gonna be a real go-getter and try to take the derivative of the third tetration, x to the x to the x. Perfectly smooth function, perfectly differentiable, and you end up with, if you do the math, x to the x to the x times x to the x times, strangely enough, ln of x squared plus ln of x plus 1 over x, which is a very odd thing. And you might even be able to see how there's like some sort of pattern going on here, but it's not at all immediately obvious what that pattern would be. And it'll actually turn out to be easier to consider taking derivatives of the tetrations of e to the x, because that will end up yielding simpler expressions. But in the next lecture on tetration, which will be on the derivatives of the functions, we will be discovering the ultimate pattern of the derivatives of these functions. So stay tuned, Papa, because that's going to be a neat generalization as well. And hopefully we'll be able to talk about the integrals as well, and maybe for the sanity of my audience, the videos won't be quite as long as this one. So thank you for watching this entire thing. If you did, this is the longest video on my channel. It took me quite a while to put together, so thank you very much for watching, and stay tuned, my mortal enemy. Goodbye.